All right, boys, hope you're doing well. In this video, I'm going to introduce you to some basic derivative rules. Okay. Now, we have been working, in fact, we had worked for quite some time. Recall that we have defined the derivative of a function, and this is new notation, f prime. That means the derivative of a function to be basically the limit as the 2 points get closer and closer and closer and closer and closer and closer together of the slope between any 2 points on that curve, right? So we spent a lot of time, even with basic functions, deriving derivatives using this limit definition. And for even the most simple functions like y equals x squared, this is a fairly cumbersome task. So what we are going to do from now on is we are going to use no longer the limit definition directly to derive or find derivatives of functions, but we are going to use some basic rules. Now these rules, directly or directly, can be shown using or verified or proved using the limit definition. Okay, which we've been tussling with for quite some time. Okay, however, we are no longer going to directly use the limit definition to derive functions. We're going to use these rules, quote unquote, shortcuts. But again, all of these shortcuts use or can be shown or proven or verified using this limit definition. Okay, so that said, here's what the derivative is. The derivative, which we note as y prime or f prime, or sometimes we see dy dx. I like that notation because it really looks like what it is. But the derivative, regardless of the notation, is the slope, the instantaneous slope, instantaneous, not average, slope of a curve, or slope of the tangent line. Same thing, as long as the point is the same, at any point. Right? So the derivative really is just the story of the slope, the story of the slope of the tangent line, the story of the instantaneous rate of change of the function at any point. Okay? So, that said, we'll derive more meaning, no pun intended, as we begin to use these. But for now, let's just think about how we can get these derivatives. So here are some derivative rules. The first is what we call the constant rule. Okay? So a constant, recall, is just a number on its own. And the constant rule says if I'm going to differentiate with respect to x, a constant, then that will be 0. And a way to think about this, we don't even need to use a limit definition, is if we had a constant function like y equals 2, let's say, right? 2 being the constant. Then remember the derivative of that constant would be the slope of that, in this case, constant function at any point. Now this horizontal line, which is a constant function, has the same slope no matter where I am. At this point, slope 0. At that point, slope 0. This point, slope 0. That point's a slope 0. That's because it's a horizontal line. So it should make sense that the story of the slope of this constant function is always going to be 0. Okay? So that's an easy way to kind of, without verification, with any limit definition, to understand why the derivative of a constant on its own, a number, 2, is equal to 0. We also have a coefficient rule. Now, a coefficient is different than a constant. And the coefficient rule says, hey, if I'm going to differentiate with respect to x, for us, we'll differentiate with respect to x for a while. Not all the time, but at first. Some multiple of a function. So c now is being multiplied by another function. So like the constant above, it's a number, But now it's a coefficient because it's being multiplied by another function. So this we call a coefficient, right? And what coefficients do is they just come along for the ride. So the derivative of 3 times sine of x, or the derivative of 4 times x squared, is going to be 3 or 4 times the derivative of y, okay? So we can, in other words, pull that coefficient out in front, multiply that by the derivative of y, the function, okay? That's called the coefficient rule. We'll do some examples in a little bit once we have some more rules to look at. Another rule which we can consider is, and this is called the sum and difference rule. Okay, and as you would expect, with a product and a quotient, it's not so true. You wouldn't expect this, but with a sum, if I'm trying to derive or differentiate a function, which we'll call it just f, plus or minus another function. So it could be x squared plus sine of x. It could be the square root of x minus x cubed. So I have two pieces, two different separate functions, which are being added or subtracted, which I'm trying to derive. And essentially what the derivative does is it distributes. So I take the derivative of the first function plus or minus, whatever that sign is, the derivative of the second function. Okay, and I'll just use that prime notation here just to spice it up a little bit. Okay, so essentially the derivative is going to distribute over the sum or difference of two functions. Okay, and now the last rule for today is going to be the power rule. And what the power rule says is that when I'm trying to derive a structure that looks like a power, so x to the nth, it could be x squared, x cubed, x to the negative 3/4, x to the 5/2, x to any power. Okay, the base is our variable x, and n is the power, which is a number. What the power rule says is the way in which we derive x to the nth is the n comes down, multiplies that by x, and then the power of n comes down 1. So I always think of this as down, down, right? The n comes down in front, becomes a coefficient, times, and then the power, which was 3, becomes a 2, or was 1/2, becomes a negative 1/2. Okay? And this is the power rule, and this also can be verified with the limit definition. That's a more complicated proof, even just for positive integer values of n. So all of these now are new rules that either directly or indirectly come from that limit definition of the derivative. Okay? So let's look at some examples that we can now use. Okay? And as we go through this couple week stretch, we're going to add more and more rules so that we can derive or differentiate or take the derivative of different types of functions. Okay? But for now, we're just going to look at basic functions for which we can use a constant, coefficient, sum difference, or power rule. So an example of that might be this. So I might say, what is the derivative with respect to x of, let's say, x cubed plus x squared plus x plus 1. Okay. And so for this problem, I'm going to use the appropriate rules. I'm going to use the sum difference rules. And again, you don't have to write all this, but I'm going to. I'm going to say, okay, by the sum difference rule, that is going to be the derivative with respect to x of x cubed plus the derivative with respect to x of x squared. I'm essentially distributing this, plus the derivative of x with respect to x plus the derivative of 1 with respect to x. Now again, you don't have to write this. This will become an easy problem to do in your head once you're familiar with this. And now I'm just going to take each derivative, right? So I'm going to derive x cubed using the power rule, right? And so what the power rule says right here is that 3 is going to come down and it turns into a 2. So the derivative of x cubed is simply the 3 comes down in front and then the power of 3 goes down 1. I just used the power rule to derive x cubed. I'm going to use the same power rule to derive x squared, right? The 2 comes down in front, x, and then the power of 2 becomes 1, right? You don't have to write the 1 power. Now, there are a couple ways to derive x. One, we can use a power rule, but I would argue, look, the derivative of a linear function, like 2x, 5x, 10x, derivative of slope, is just going to be 2, 5, or 10. So I would say, what's a derivative or slope of y equals x? And you would say, well, duh, that's just 1, because it's a line. That's what the slope is. You could also do this with the power rule. The 1 would come down, multiply by x. 1 goes down 1 to 0. And of course, x to the 0 is 1. Okay, now when I derive the 1, I'm going to use my constant rule, which says the derivative of a constant is 0. So the derivative of that 1 is just 0. Right? So here is my answer. The derivative of my original cubic function is this quadratic function. Okay? Power rule, power rule, power rule, or linear if you think about it. And then this is my constant rule here to get 0. Okay? Let's look at a little harder problem. I might say, all right, well, what would the derivative of, let's say, 4 over x plus 2 over 3x squared plus 6 be? Okay, let's spice it up. Let's make that a minus. Get a little crazy. Okay, so in my head, I'm thinking, okay, I'm going to derive the 4 over x using the sum difference rule, plus I'm going to derive 2 over 3x squared with respect to x, and I'm going to derive 6 with respect to x. That's a sum difference rule. Okay. Now, here's a little trick. We only know now, and we'll know more rules later, but even if we had no other rules, this is the easiest way to do this problem. I'm going to recognize that 4 over x, before I use my calculus, can be rewritten as 4 times a power of x. So I'm not going to derive yet, no calculus yet. That's just 4x to the negative 1. Ooh. Plus, I'm going to look for the same thing with this term, 2 over 3x squared. 2 over 3x squared, look, there's my coefficient, 2/3. I'm just going to rewrite it, no calculus yet, times x. And because it's squared in the bottom, that's to the negative 2 power. Ooh, easy. Okay, and I'll soon derive this 6 later, next step. But I haven't done any calculus yet. I'm just rewriting each term as a coefficient, 4, times the power of x, x to the negative 1. I'm rewriting this second term as a coefficient, 2/3, times a power of x, x to the negative 2. No calculus yet. Okay, now I'm going to derive using both my coefficient and power rule, at least for the first 2 terms. And the derivative of 4 is my coefficient, so it's going to be 4 times the derivative of x to the negative 1. Now the derivative of x to the negative 1, use the power rule, so the negative comes down in front, and then I bump the power, subtract 1, so negative 1 minus 1 is negative 2. Plus the 2/3 is the coefficient, comes along for a ride, times what's going to go here is the derivative of x to the negative 2, which using the power rule, negative 2 comes down, the negative 2 minus 1 goes down to negative 3. There's your power rule. Minus, now the derivative of 6 with respect to x is 0. There's my constant rule. Okay. Now the only thing I can do now is clean it up a little bit. I'm going to rewrite this first term as negative 4 on top, and because x is to the negative 2, I'll write that x squared downstairs. Minus, plus minus becomes minus. 2 times 2 is 4, so there's a 4 up top, and on the bottom there's a 3, and there's an x to the negative 3, which is x cubed on the bottom. Okay, so this is the function, the story of the slope of my original function, which is this, when rewritten, this guy, or really I suppose this guy, at any point. Okay, so again I'm just using coefficient, power rule, coefficient, power rule, coefficient, power rule. And then here with the 6, constant rule. Okay, again here are the rules. Okay? And we will add more and more of these rules as we derive more and more types of functions. Have fun.